Hi, my name is Nikhilesh. I'm an applications engineer with the Analog Solutions Group at Semiconductor. Today, I'll be introducing the FAN 6248, an advanced synchronous rectifier controller optimized for resonant LLC converters. Let's start by looking at some of the key features of the FAN 6248. Shown to the bottom right is a block diagram of the internal IC architecture. The FAN 6248 features an anti-shoot-through control that ensures reliable SR operation. The unique feature of this new controller is the adaptive dead time control algorithm. This technique adjusts the synchronous rectifier turn-off instant to maintain a constant dead time regardless of the output load and stray parasitic inductance. This helps minimize the body diode conduction and maximize efficiency. The FAN 6248 controller detects synchronous rectifier current inversion that occurs when capacitive currents prematurely turn on the MOSFET at light load. Such operation is prevented by increasing the turn-on delay under light load conditions, providing safe, stable, and efficient operation. The controller has an adaptive on-time circuit for better noise immunity. Dedicated 100-volt rated inputs for sensing the drain and source voltage of each SR MOSFET. It supports high-frequency operation up to 700 kHz. Low operating current in green mode, typically 350 microamps. Shown here is a typical application circuit. On the primary side, there is an LLC controller. On the secondary side, we have a very simple configuration comprising of the FAN 6248 controller and two external resistors to drive the two synchronous rectifier MOSFETs, M1 and M2. As you can see, it is a highly integrated controller requiring minimum external components. The SR turnoff algorithm in FAN 6248 is based on a mixed type control, utilizing both real-time information received by sensing the drain node of the MOSFET and previous cycle information. The implementation can be easily analyzed using a simplified circuit in which the turn-off event is determined by comparing the drain voltage of the MOSFET to a virtual turn-off threshold. The following slide describes the adaptive dead time control scheme. When the dead time is found to be greater than the desired 200 nanoseconds, the offset voltage is increased. As a result, the virtual VT-off threshold is raised, leading to a longer SR conduction period and shorter dead time. When the dead time falls below the 200 nanoseconds, the comparator threshold virtual VTH-off is lowered, resulting in a shorter SR conduction period and longer dead time. Hence, the algorithm maintains the dead time at around 200 nanoseconds regardless of the output load and parasitic inductance. The FAN 6248 has a minimum on-time circuit. The controller sets the minimum on-time at 50% of the previous cycle conduction period. Turn-off triggers are ignored during this interval. SR current inversion detection. At light load, capacitive currents caused due to parasitics can trigger an SR turn-on event. Enabling the synchronous rectifier under such conditions could lead to reverse current flow from the output capacitor back towards the SR. The FAN 6248 controller provides an increased turn-on delay at light loads to prevent such an event. The turn-on delay is increased from 80 nanoseconds at full load operation to 380 nanoseconds at light load. The SR controller enters green mode operation when it does not detect switching for a period longer than 240 microseconds. While in green mode, the controller stops all switching operation to reduce the operating current and minimize power consumption. When 11 consecutive switching cycles are detected, the SR drive pulses are enabled again. The operating current in green mode is 350 microamps. Shown in this efficiency plot is a comparison of the performance of FAN 6248 versus some competitor parts. As you can see, the FAN 6248 provides higher efficiency and best-in-class performance. So let's power up our evaluation board and look at some waveforms. We'll start by turning on the 17.5 volts bias voltage for the primary side LLC converter. We have an electronic load enabled for 10 amps. And then we'll turn on our high voltage power supply for 400 volt input. So as you can see, the supply ramps up and we have 394 volts input and we have a regulated 12 volt output. So now let's increase the load to 15 amps. So we have 15 amps on the output. That corresponds to around 180 watts. Let's stop our scope. So on channel 1 and channel 3, that's the yellow and purple waveforms, I have the SR gate drive signals. And on channels 2 and 4, I have the corresponding drain source voltages of the secondary side SR MOSFETs. So let's begin by measuring the dead time. So as I mentioned, the yellow signal is our SR gate drive, and it turns off at this instant right here. The moment the secondary side current goes to 0 is right here. So the dead time measures around 204 nanoseconds. Let's also measure the turn-on delay at 180 watts. So the waveform in green is the drain source voltage of the MOSFET. The moment that's pulled low indicates that the body diode is forced into conduction. And the delay from when that instant till the SR gate drive goes high is 120 nanoseconds. Turn-on delay. Let's examine the same waveforms at lighter load. So I'm going to run my scope, and I'm going to reduce the load. Let's go to 2 amps. 2 amps, we have a regulated 12 volt output. This corresponds to around 24 watts. I'm going to stop our scope and look at the same 2 measurements. So if I zoom in, the yellow waveform is the gate drive signal going low, indicating turn off of the SR. The moment the secondary side current goes to 0, it's measuring around 310 nanoseconds. Let's also measure the turn-on delay at light load. So the green waveform gets pulled low at this instant here, and then the SR gate drive goes high over here. So that measures approximately 460 nanoseconds. So that indicates that at light load there's an increased turn-on delay for the SR gate drive.